Connect two network switches with multiple cables, and you might think you're doubling your speed. Instead, you create a Layer 2 network loop. Data packets circulate endlessly until the resulting traffic jam takes down the entire network. This chart outlines what happens next. The network's built-in defense mechanism, Spanning Tree Protocol, detects the loop and simply shuts down the extra links. You connected 4 cables, but the network only lets you use 1. There is a way around this block. If we configure a feature called EtherChannel, we trick the switches into treating those 4 separate physical cables as a single logical link. This logical bundle fixes 3 problems at once. Spanning Tree stays happy because it only sees 1 path. You get the aggregate bandwidth of all 4 links, and if 1 physical cable snaps, the logical connection stays up, routing traffic over the surviving ports. But switches don't automatically know they are supposed to group these cables together. You have to explicitly tell them how to form the bundle. You have 3 distinct options to build this connection: static EtherChannel, the LACP open standard, and Cisco's proprietary PAgP protocol. EtherChannel relies on a consistent communication language between 2 switches. Using the wrong protocol dialect can crash the network entirely. Let's start with the first method, static EtherChannel. In a switch's command line, this is simply known as mode on. Static mode does exactly what the name implies. It forcefully bundles the ports right away. It completely skips any kind of introductory handshake. This diagram shows the only way static mode works. If switch A is configured to on and switch B is configured to on, the links slam into place and the bundle forms. Because there are no safety checks or continuous hello messages crossing the wire, a static port has no mechanism to verify if the device on the other end is actually configured correctly. If someone unplugs a cable and moves it to the wrong port, the switch stays blind to the error. It keeps sending data down a dead end, resulting in dropped packets and silent network failures that are incredibly tedious to troubleshoot. Typing mode on is fast, but you are forcing a connection while blindfolded, hoping the other side is ready for the traffic. To solve that blind connection problem, enterprise networks use the Link Aggregation Control Protocol, or LACP. This is an open standard, meaning it works securely across equipment from almost any vendor. LACP replaces the blind force of static mode with a negotiation. Before any user data flows, the switches exchange LACP protocol messages to verify partner identity and confirm that these specific ports belong in the same bundle. A port using LACP can be set to active mode. It aggressively initiates the conversation, asking the other switch to form the channel. The alternative is passive mode. A passive port listens for incoming LACP messages and will only join a bundle if spoken to first. Active plus active works perfectly. Both switches initiate the handshake and verify each other. Active plus passive also succeeds. The active switch starts the handshake and the passive switch responds. But passive plus passive fails. Since both sides wait, the link stays down. By requiring an active negotiation, LACP builds a dynamic safety net. If a cable goes to the wrong switch, the LACP handshake fails, and the system automatically drops that bad link to protect the rest of your network. The third option is PAgP, the Port Aggregation Protocol. This is Cisco's proprietary alternative, built specifically for networks running entirely on Cisco hardware. Mechanically, PAgP does the same job as LACP, but uses different terminology. Instead of active, a PAgP port is set to desirable to initiate negotiation, and instead of passive, it uses auto to act as the listener waiting for a request. The rules mirror the LACP standard perfectly. Desirable on both sides works, desirable on one side and auto on the other works, but pair auto with auto and the connection fails in silence. PAgP is highly reliable if you are working in an isolated, legacy Cisco environment. But tying your infrastructure to a proprietary standard today limits your ability to integrate a different vendor's firewall, server, or switch down the line. When engineers configure these channels, the most common way they cause an outage is by trying to mix these different modes across a single connection. Setting one switch to LACP and the other to PAgP makes their protocol messages collide and shatter. Mixing a static port with LACP is equally destructive. The LACP side waits for a handshake, while the static side blindly forces the connection, triggering an error. The exact same failure happens if you make PAgP desirable with static on. There is zero flexibility here. To form a logical connection, both endpoints must rigorously commit to the exact same operational language. This quadrant maps exactly how you should choose your protocol, plotting the safety of dynamic negotiation against vendor flexibility. PAgP lands in the top left. It gives you the high safety of an active negotiation, but poor vendor flexibility. You only deploy this to maintain older, isolated Cisco networks. Static mode sits in the bottom right. It works with almost anything, but gives you zero safety. You use this strictly as a last resort when connecting a basic device that lacks the processing power to run a negotiation protocol. LACP sits in the top right. It provides the strict safety checks of continuous negotiation alongside total multi-vendor support. Standardizing on LACP Active removes the passive waiting game, protects against blind misconfigurations, and ensures your network can scale regardless of future hardware. The cleanest way to manage this is to configure your logical port channel interface first. Apply your VLAN and trunk settings to the primary bundle, and let those configurations automatically trickle down to the individual member links. A resilient EtherChannel requires two things: the dynamic intelligence of an open protocol like LACP, and the strict operational discipline to configure the physical ports consistently.